Alright, so first things first, exponential growth functions. We've talked about exponential growth last unit. We talked about exponential decay last unit. We're going to go a little bit more in depth on them. Exponential growth, our equation, right? The format is y equals a times b to the x. And we did that same thing except we had 1 minus or 1 plus r in there. Right? That's because it's exponential growth when b is greater than 1. That's why last unit we had a times 1 plus r, to make our b value greater than 1. That meant it was exponential growth. So in this unit we're going to talk about y equals a times b to the x, and growth happens when b is greater than 1. Alright? So, our exponential growth, we said it happens when b is greater than 1. Every exponential growth curve will look something like that. It may be a little bit flatter, it may be a little more steep, it may be shifted left to right, but every single one is going to go up rapidly as we go left to right. Okay, that's just how the exponential growth curves look. Now, what I want you to do is, in your graphing calculator, I want you to plug these 3 equations in your y equals. I think we might have to change our windows a little bit, what do we have here? Yeah. So once you're going to put in a y equals, I'll put them in mine as well so you can see it up here if you don't have your calculator today. Where are we at? 2 to the x, 5 to the x, 4 times 3 to the x. Alright, so before you can graph them, let's change our windows. We're going to go negative 10 to 10 for both x minimum, x maximum, and y minimum, y maximum. And your scales should both be set at 1. Just so we can see the whole thing. Okay, so your window should look like mine. Negative 10 to 10 with a scale of 1. Negative 10 to 10 with a scale of 1. Those top 6 are the only things we should change. We should never touch anything below the y scale. Should never change anything down there. Alright? We all have our window set?
Yeah.
Give about 5 seconds. Alright, so if you hit graph then, once you've set your window, there should be 3 graphs that pop up. Right?
Mine's frozen.
Yours just frozen. How do you hit the
Oh.
graph button?
Oh, I paused it. I forgot you paused it. So weird. How do you pause it? Oh, it just frozen. Here's the center.
Yes, sir. Guys, are all 3 of those exponential growth?
Yes.
How do we know? All go up.
They're all greater than 1. Yes. Greater than 1.
Okay, so that should answer your first question. Are they all exponential growth? Yes. So, second question. What makes them growth? How do you know they're all growth? They're all going up. But like what number? If we look at all of them, y equals 2 to the x. Y equals 5 to the x. Y equals 4 times 3 to the x. We just talked about it. What number tells us that would be growth? If we looked at them without even plugging them into our calculator. If I looked at these, I didn't put them in my calculator. I just looked at them. How could I tell that they're growth just by staring at them?
All positive.
Well, someone back there said it.
B is greater than 1.
B is greater than 1, right? Just because they're positive doesn't make them growth. B, our B value, is greater than 1. Right? We had just said in the slide before, if B is greater than 1, I know it's going to be growth. Alright, so I plugged them all in. We got something that looked like that, right? Are they all exponential growth? Yes. What do the numbers in front do to our graphs? Are all our graphs the same? No. What happens is, if we look at mine back here again, right, our first one was 2 to the x. The red one was 5 to the x. The black one was 4 times 3 to the x. what happens is the A value, and I'll write this down on mine too, if I can get it to go down. What do the numbers in front of the graphs do? The A value makes them steeper. So the A value makes them steeper. Right? You'll notice that the 4 times 3 to the x graph goes up way quicker than the other two graphs. Right? When we have A values in front, the bigger the A value, the steeper it's going to get. Alright, like I said before though guys, we're not going to ask you to actually graph these. We're going to ask you to match a graph with an equation. So you just punch it in your calculator and match it. Or tell us whether it's growth or decay. Alright? I think the last question says, why don't any of these graphs cross the x-axis? Why don't they cross the x-axis? What? They're not negative, right? If we look here, 2 is changing. Will 2 ever be negative no matter what exponent I use for x? No. If I have a negative exponent, but if you look at my graph, do I ever cross that x-axis? No, so I'm never going below it. I'm never getting to 0. So we have what we call a horizontal asymptote. Horizontal asymptote. A horizontal asymptote is an imaginary line that stops it from crossing. So like in this case, our x-axis is a horizontal asymptote. We will never cross it with exponential growth. It'll never have a y value that's negative. Alright, so there's a horizontal asymptote. Y will never be equal to 0 or negative. If you look, it'll get really close to 0, but it will never get to 0. When I have negative numbers here, it's going to turn into like 1/5, 1/25, 1 over 125. It's going to get really close to 0, but it never actually gets there. It can never become a negative number for an answer. Alright? Alright. Okay. Same thing for decay, except now, oh, didn't highlight. Highlighter. It's the same function, but it's going to be decay when we're between 0 and 1 for b. And when b is between 0 and 1, once again it's still positive, but now it's less than 1, it's going to be exponential decay. And exponential decay is just the opposite of growth. Right? It starts out really tall and comes down fast and flattens out. From left to right it goes down. Decay goes down, growth goes up from left to right. Alright, so our function is the same, y equals 8 times b to the x. We know it's decay when b is between 0 and 1. So growth happens when b is greater than 1. Decay happens when it's between 0 and 1. Alright. If I'm looking at these 3 functions right here, first of all, are they all going to be decay? Yes. How can we tell that? The b, not just less than 1 though. Be careful when you say that, because that can mean a negative number, right? We know that b is between 0 and 1 for all of those numbers. So once again, b is between 0 and 1. Actually, I think that's one of the questions here. What number makes them decay? Well, b being between 0 and 1. Okay, I want you to go ahead and once again put those in your calculator. I just want you to get used to putting these in your calculator and seeing them on your graph. So like I said, on something really important, you may have to match certain graphs with equations. But what do I know, right? So I want you to try and put them in there. I'll put them in on mine. Y equals 1/2 the x. Oops, I don't want that. What was the other one? 1/4 the x. 6 times 1/5. Okay.
We can.
It's thinking. That's not right. Alright, did we all get graphs that look like that? They are all exponential decay, right? They start from left to right, they go down. Now, the same thing happens, right? What do the numbers in front do? Well, A makes it get steeper, right? I put a 6 in front of this black one, and it got way steeper coming down before it flattened out. So our A value, once again, it makes it steeper. As A gets bigger, it gets steeper. Now as we change our B value, it shifts left and right, but that A value makes it get steeper. Or, vice versa, if it got smaller, it'd make it get, what's less steep? I can't think of the word right now. Flatter. Be flatter. Okay? Same thing here, guys. We have a horizontal asymptote on the x-axis. It'll get really, really, really close to the x-axis, but it will never cross our x-axis. It'll never equal 0. It'll never equal a negative. Alright, so we have a horizontal asymptote here. Do you need to remember that? No. It's a great math term because you'll probably need it next year in either FST or pre-calc. You'll deal with asymptotes. But are we going to need it? No. Alright? Guys, any questions on that stuff? Like I said, we're not going to ask you to physically graph on a piece of paper. We may just ask you to match these with their correct equations. Okay? Any questions? We good? Okay. So let's keep going. Examples. For each equation below, identify the equation as exponential growth or decay. Well, before we even do that, what's our rule? How do we know it's growth? If b is greater than 1. How do you know it's decay? Between 0 and 1. Okay, so if I look at these problems, just looking at them. Y equals a times b to the x, right? That's our equation. My b value here is going to be 1.67. Correct? Is that greater than 1 or between 0 and 1? Greater than 1, so I know it's going to be growth. That's all it's asking us to do is look at the b value and tell us, is it going to be growth or decay? The second one, 0.8 times 0.54 to the x. Well, what's my b value? 0.54. Is that greater than 1? No, it is between 0 and 1, so this would be decay. Y equals 4.5 times 4 to the negative x. What do you think? How many of us think it's growth? How many of us think it's decay? How many of us didn't answer? We need to be very careful with problems like this, guys. In our equation, we have b to the positive x. Do we have a positive exponent right now? How do you make it a positive exponent? We flip what's in the parentheses, right? So this becomes y equals 4.5, because this was 4 over 1, to the 1 over 4 to the positive x. Be very careful. We need a positive exponent. So if we have a positive exponent, we have 1/4 for b. Is that greater than 1? No, so it's going to be decay. Alright, y equals 2 times 8 over 5 to the x power. Growth, right? It's positive. 8 over 5 is greater than 1, so it's growth. Alright, any questions on that? That was pretty easy, right?
Yeah.
Alright, we're going to kind of fly to the next couple pieces here. For each graph below, identify it as growth or decay, estimate its initial value. Well, here's a hint. Initial value is when we cross the y-axis, when x equals 0, otherwise known as our y-intercept. So initial value is our y-intercept. Right? It's when x equals 0. Okay, so if you look at the first graph, is this growth or decay? Growth, right? From left to right, it is going up. So this is growth. And then it says estimate the initial value. So we're going to estimate where does it cross our y-axis? Approximately 2.5. Guys, if you're off a little bit in your estimates, not a big deal. The important part is knowing which one's growth, which one's decay. All right? The second problem, if I look here, is this growth or decay? Growth, right? From left to right, we're going up. So this is growth. We're going to look right about here, just underneath 7 it crosses. So approximately, what do you think? 6.8, perfect. Approximately 6.8. If you want to put 6.7, good. It says estimate. It doesn't give us a nice value there. Then Aubin. My last one. Is this growth or decay?
Decay.
How do you know that? It's going down, right? If I look at it from left to right, it's coming down. All right? And what's an initial value? 8? Approximately? That works for me. Okay. Like I said, guys, big thing here is being able to tell from a graph whether it's growth or decay. All right. Questions? What about a table? Can you tell me from a table if it's growth or decay? What do you think? Well, yeah. How do we do it though? Natalie, what do you think? The first one. What do you think it's going to be?
I think as the x increases and the y decreases, it would be decay.
Perfect, right? Oops, that's going the wrong way. As x increases, or as x goes up, right? That'd be like going left to right on our graph. If y goes down, it's going to be decay. Okay, I'm having trouble spelling. Right? As x goes up, so as we go left to right on our graph, if our y value is going down, that means it's going to be decay. Well, if my x goes up and my y goes up at the same time, then it's going to be growth. Get out of my way. All right. Does that make sense? As we go left to right on our graph, as our x gets bigger, if y goes up, it's growth. If it goes down, it's decay. All right, our last one, Tui.
Growth.
How do you know that?
Y increases.
Y is increasing as x is increasing. Good. Any questions on finding it from a table? Whether it's growth or decay? No? All right. Then, we're going to talk a little bit about log functions, because we said logs are the opposite of exponentials, right? So, like I said, we may ask you to match some of these log functions. Just like we said, we might have to match some exponentials, but we're not going to ask you to graph them. All right? So, our exponential functions, they go up from left to right, they go down from left to right. The log functions are an exact mirror across x equals y, because they're the inverse. All right? So if we're looking at a log function, it's either starting here and going up, or it's going the opposite way. I can't even draw it on it right now. It'll be going up and like this. So our y-axis becomes our asymptote for log functions. So if you look at them, exponentials and log functions are mirrors of each other. That's the big thing we need to get from this. Right? Just like how we solve an exponential with a log, or a log with an exponential, they're mirrors of each other. They're graphs. They are mirror images of each other. How do they compare? They are mirror images of each other. Mirror images of each other. And do we see any asymptotes? Same thing, like with the exponentials, we're still going to have our x-axis as our asymptote. The log functions, since they're a mirror, we flip it, the y-axis becomes an asymptote. Alright? Like I said, guys, this is probably one of my least favorite days in the unit. Right? There's not a whole lot of actually doing. We're just trying to look at them. Alright. Any questions on that? We good? I think we have one more thing to do. I think it's one application problem, we're done. It's got 3 parts, but